description of the drying region. Okay, so we have understood that when the drying takes place from a food material, the rate of drying, that means rate of moisture removal, okay, during the whole drying process doesn't remain constant, and that is because of the presence of different nature of water within the food. So why we are saying the different nature in a means that when you start drying the food material, initially you have a the amount of moisture present in the food, it acts like a free water. That means you have a water in a pan, just water in a pan or in a bucket. Okay, so when this water is being removed, so during that time, okay, it maintains the constant rate period. Okay, and you think of that, there is a continuous film of water exist on the food surface, and that is being evaporated. So the moment it is being evaporated, the same amount of moisture is also being supplied from the you know from the food material. I mean, within the food material, whatever is water is there, that is also being transferred from the food material to the food surface, and that is also getting evaporated. Okay, so like rate of evaporation is basically equals to the rate of supply of the water within the food. Okay, so during that period we are having the constant rate drying. Okay, now the moment it reaches to critical moisture content, so the some moisture content, okay, that we call a critical moisture content. Okay, sorry. So from after the critical moisture content, the drying rate decreases. Why? Because the movement of nature of the movement of the water. In this region, we are having the unsaturated surface drying. Okay, so what is the unsaturated surface drying? So what we are saying that there is a continuous film of water. Now the when the water is evaporated, so water is the way or at the rate at which the water is getting evaporated, the water is not supplied from the food material at not that at rate. Okay, that means in the surface of the food product you will be having lot of dry region. Okay, and this dry region will keep on increasing. Okay, in the falling rate what happens, so the water within the food product, it moves by the capillary action and plus the diffusion. So we are having two lines, you remember we had a, I will just show you over here, straight line, and in is the curvy lines, that is the concave upward lines. So in the first region, so the straight line, okay, in the straight line we are having fast falling rate. So in the fast falling rate is the capillary controlled one. So if you see how the capillary controls look like, so let's say, so if you have just water, okay, so if you have a water and if you put a small pipe, what will happen? What will happen if you put a small pipe? So water will rise through this column because of the capillary action. Okay, so within the food material there are a lot of interconnecting ports and capillaries. So food water within the food material, they will rise up to the surface due to this capillary movement of the water. Okay, now when this one is also receding, okay, so there is not enough water that can be moved due to the capillary action. So what happens, so see, let's say this is the food surface, so here it's the capillary water is rising, so it also going down over the period because of the evaporation. So to fill this void in the capillary, so water, so air gets sucked in, so water enters to fill the void. Okay, so when water enters to fill the void, okay, so when it reaches to, let's say, point D, so it's a sufficient at sufficiently low amount of moisture. Okay, from D to E. Okay, so there is another mode of water movement, that is called the diffusion controlled one. Okay, so now we will talk about the diffusion controlled one. So diffusion controlled drying. Okay. So we talked about there is a continuous film of water, okay, around the particle. Okay. So when, okay, I would say when the moisture content in food reaches to point B, okay, the amount of water is very low, okay, and there is no continuous film of water exists around food particle food particles, okay. So okay, so due to this insufficient of due to the insufficient sorry amount of water, capillary flow will not occur, and um, and uh, movement of moisture movement of moisture mm, occurs by vapor diffusion, okay, in the pore pores, okay, and rate of conduction of heat in solid food dominates the moisture movement. So this occurs in second falling rate drying. Okay, so this occurs in second falling rate drying period. Okay, is it clear? See what happens. So you have a food material. There are capillaries, pores, and all, and they are interconnected. Okay. Now what happens? So when it reaches to point D, the moisture content within the food product is sufficiently low. Okay, but it's not that level that we are targeting. Okay, it is sufficiently low, and it cannot the moisture movement cannot occur due to the capillary flow. So what happens here? It's almost all the moistures are gone. Now the products becomes very hot. So that's why we are saying that conduction heat transfer dominates the moisture movement. So when it becomes hot, what happens? So whatever amount of moistures are left within the food, they turns into a vapor. Okay, when it turns into a vapor, so it try to move along the pores. Okay, and the moment it reaches to the some colder zone, okay, some colder zone, so it's because, see, this is the conduction heating. So conduction heating is outside to inside. So the outside will be, hot first, then it will be slowly moving to the core region. Okay, so moisture, the region where it is, warmest one, or I would say the hotter zone, that region, that it will be it will be developing the vapors, and when it will be moving, within the food product, it will try to move upwards. So when it will reaches to some colder zone, it will try to condense. Again, when it will, that part will be hot, again it will turn into a vapor and it will try to move on. So this is called the diffusion control drying. Okay, so this is called diffusion control drying, and it occurs in the second falling rate period. Okay, is it clear? Is it clear? So here, if you see, this one is the diffusion control. Okay, all right. Now what we will do, we will look at the mathematical expression, okay, to calculate the rate of drying for all the periods. Okay, so constant rate drying and falling rate drying. So why the rate of drying is required? Because if you are able to calculate the rate of drying, then you will be able to calculate the time required to reduce the moisture content from a certain level to a desired level. Okay, so that is what now we will be focusing at. So I will start then in a new page. Okay, so rate of drying, at constant rate drying period. Okay, at constant rate drying period. So let's draw the picture. So let's say we have so A, this is B, C, this is D, and this is E. So this is time, and this is free moisture we are saying here. Sorry, then if we say free moisture, then what I have to do is, okay, free moisture, capital X. Okay, so let's say this is A, B, okay, C. So B to C is the constant rate drying period, and usually this one is linear. It's a constant rate. So rate of, that means rate of moisture removal is same wherever you look at along the line. That means rate of moisture removal means what is that? Dx by dt, right? The slope of this line BC. Okay, so dx by dt will remain constant in this region B to C. Okay, C to D also looks like a straight line, but I will rather, what I would do, you will change a little bit, maybe like C to D. Okay, So C2D during this, actually it's not representative quite good. So what I would say, B to C straight line, then is E. Okay. So here B to C, constant rate drying period. That means dx by dt is the rate of moisture removal. Okay. So if you take any point x1 minus x2 divided by t1 minus t2. Okay. So let's say this is x1 and this is x2. X1 and x2. Let's say, so this corresponding time are t1 and t2. Okay, so t1 and t2. Okay, all right. So now if we draw the, free moisture versus rate, so how does it look like? We already know it. So let's say this is constant rate, falling rate. This is E. Okay, so we are having free moisture, not total moisture. Okay, X. B, C, D, E. So this is, we are saying RC. So this is rate. So this one is RC. That means constant rate drying. This is the, rate for the constant rate drying period. So it remains constant along this line. You see it's parallel to the x-axis. Okay. That means here it is. So let's say from XB to when it comes to XC. Okay. During this period, it remains as a constant rate drying period. Clear? Is it clear? Yes? Okay. Now what we are saying, so just to for you, so recalling, so free moisture X equals to Xt minus X equilibrium. Okay, so free moisture is usual in kg H2O per kg dry solid kg ds. Okay, and where X total is total moisture W minus Ws divided by Ws, and Xe equals to We minus Ws divided by Ws. Okay, so there carries the usual, notation. Okay, so rate of drying, okay, for constant rate period, okay, is expressed, okay, as kgH2O per meter square per hour. Now what is kg? Kg means how much moisture you are removing. Now what is per meter square? Per meter square means per meter square of exposed surface area. Let's say you have a, say, okay, let's say I have this tray. Okay, now this tray I have put the food. up to this level. Okay. Now, so tray has got some dimensions like this. Okay, if I draw it like this. So what is the, see, this part is blocked. This has the solid. This is solid. This is solid. Here it is solid. So exposed surface area is the this one. Okay. So that's the exposed surface area. Okay. So let's say this is A. A is the exposed surface area of food in meter square. Okay. Now, when we are saying rate of drying, so this is RC. Okay, is the constant, sorry, constant rate drying. Okay, or I would say, I would rather write it as a rate of drying in constant rate drying period. Okay, so this is in kg H2O per meter square hour. Okay, now how it is written? We expressed it as a equals to minus Ws by A dx dt. Okay, so dx dt is slope of this line, nothing more than that. Okay, so this is the rate of moisture removal. Okay, multiplied by Ws, that giving you the solid divided by A. A is the exposed surface area. Now what is how it is coming in finally with this one? So what is dx is the free moisture content. So if you look at the unit, it is kg moisture kg H2O per kg dry solid. This one dx by time, that means let's say hour. This one is the dry solid, kg dry solid divided by meter square. Kg dry solid cancels out, kg H2O per meter square hour. Clear? All right. So Ws is the kg dry solid. Okay, kg dry solid. Let's say if I take here is the x1 and x2. Let's say if you have a x1 equals to 0.350 at T1 equals to 1.68. Okay, x2 equals to 0.325 at T2 equals to 2.04 hour. Now why we have put negative over here? See, dx by dt, that means if you move along this line, if the time is increasing, the moisture content is decreasing. In order to whole thing positive, we are putting negative sign over here. All right. Okay, so if you have any question, please feel free to ask me. Okay, so then what will happen? So x1 minus x2 divided by t1 minus t2 equals to 0.350 minus 0.325 divided by 1.68 minus 2.04. How much this is? This is coming. So 0.0694, right? Yeah. Kg H2O per kg dry solid. Okay. Let's say Ws by A equals to, okay. Let's say I'm just saying you 21 or 20, or let's say 21.5 kg dry solid per meter square. Okay. So you can easily calculate the RC value, the rate of drying. Okay, so this is 21.5 multiplied by 0.0694. Whatever answer is, you will be able to calculate. Okay, sorry, this is in hour, so you have time factor. Okay, so this is the result. So now RC equals to minus WS by A dx dt, right? So what we can do, RC dt, okay? So let's say so here if you really see, so here the drying process starts mainly. Okay, let's say this one we are taking as a T1. Here mainly the drying process starts. Okay, after the initial warm up period. So let's say we are saying T1 equals to T1 to T2. We are at first we will be using the general notation. Okay, minus Ws by A dx. So it is x1 to x2, right? So therefore RC T2 minus T1 equals to minus Ws by A x2 minus x1, right? Okay. Then RC, so let's say this is T2 minus, sorry, T2 minus T1 equals to minus Ws by A. So let's make it positive, x1 minus x2. So T2 minus T1 equals to Ws by ARC x1 minus x2, right? So this is the time requirement. So let's say say T2 equals to T and T1 equals to 0 as drying starts at T1 equals to 0 time. Okay. So therefore TC, let's say this is TC, okay, equals to Ws by ARC x1 minus x2. So this is the TC equals to time required during constant rate drying period. Clear? Any question? Any question? Any question? Any question? So this is the your general thing. Now see, so x1 could be here anywhere. Okay. So basically at the very beginning we are saying this is x1. That means if you look at here, this is corresponding to xb, and the final one is the xc, right? So we can also write this one equals to Tc equals to Ws by ARC xb minus xc, because this is the constant rate drying period from xb to xc. So this is the initial moisture content xb, which is x1, and final one is xc, that is equals to x2. Okay. All right. Any question? Any question? Okay. So let's say now you think that as I was mentioning, so let's say I have a food. So okay. So we have food here in this tray. Okay, in this tray we have food, and hot air is passing over the food surface. Okay. So what is the exposed area? So this is the exposed area. So this is the exposed area. So here it is solid, solid, solid. All the other side are actually closed. So this is, I am giving you one example. So there are, to increase the, drying rate, what we usually do, we expose the bottom part also. But I am giving you the very, typical and simplest one. Okay. Now, so this is the area. So this is the area. Okay. Now let's say this is the thickness of the food material. Let's say this is the 2 delta. Okay. Let's say thickness of food in tray equals to 2 delta. Okay. Exposed surface area equals to A. Okay. Now tell me what would be the volume. So volume, let's say V equals to A multiplied by 2 delta. Right. This is the area and multiplied by this thickness. So this is in meter cube, this is in meter, this is in meter square. Okay. Let's say bulk density of food equals to rho B kg per meter cube. Now what is bulk density? So bulk density is, let's say you have a moist food. Let's say you have a 100 kg. 100 kg of moist food. Now this one is being loaded in a tray. Okay. So this 100 kg of moist food is being loaded in a tray. Okay. And the tray has volume of, let's say, 2 meter cube. 2 meter cube volume. Say, I'm just giving you example. So basically you are taking the tray and you are putting the 100 kg in the 2 meter cube of volume. Okay. So bulk density, rho B will be 100 by 2. It means 500 kg per meter cube. That is the bulk density. Okay. That's the bulk density. Okay. Now solid density of food. That means here what is saying that how much food is there in bulk per unit volume of the container. Okay. So solid density of the food, let's say, equals to rho S kg per meter cube. Okay. So bulk density is, so this is the moist food. Okay. That means bulk density we can write weight of the material divided by V. Right? Weight of the material or mass of the material divided by V. So this is weight of the water plus weight of the solid divided by V. Okay. This one we can also write WW divided by WS plus 1 divided by V by WS. Now this, so this is actually we are saying W by V. Okay. And this one is WS by V. That means now we have a 100 kg. Let's say in the 100 kg you have a 80% moisture. Right, you have 80% moisture. When all the moisture will be removed, you will be left with the 20 kg of dry solid. Then what would be the rho S? Let's say 100 kg food with 80% weight basis moisture content. So this one will be 20 divided by 2, 10 kg per meter cube. That means it has become dry, and most of the places are become, so we are removing the moisture. So because it also counts the mass of the moisture, here only you are left with the dry solid. So that's why it's become 20 by 2, 10 kg per meter cube. It reduced. Okay. So what we will do now, if you write Ws by V, okay, rho B divided by 1 plus, what is this one? So if you take this one over here, it will be V by Ws. Now we are doing Ws by V, then rho B by 1 by W by Ws. So this is rho B by 1 plus moisture content in dry basis. Okay. So therefore rho S equals to rho B divided by 1 plus moisture content in dry basis. Okay, so this is one expression will be very useful while we will be solving the problems. Okay, now TC. So what is TC? Ws by ARC XB minus XC. Okay, now what is Ws? Ws will be rho S multiplied by V. So this is rho S multiplied by 2 delta into A. So we can write rho S 2 delta into A XB minus XC divided by ARC. So A got cancelled. So TC becomes 2 delta rho S divided by RC XB minus XC. Any question? Any question? Any question? Any question?
No, sir.
Okay. All right. So now we know what is the expression to calculate the time using the rate of drying during the constant rate drying period. Now we will move. So now we have reached to point XC. Now how do you tackle from XC to XD? So this is the falling rate period for the fast falling rate region. Okay. So that part we have to focus now. All right. Now how can we do that? So you see during this period actually your rate is changing. If you take any point, although here is the XC and we are trying to reach to final free moisture content to XD, but during if you move along this line the rate is actually changing. Okay, now how to solve this one? Okay, so this is the first case. Let's say this is the first case. Okay, second, rate of drying in fast falling rate region. Okay, let's draw the picture one more time. So so here I have X, B. Now what we will do to solve this problem, we will not consider the second falling rate while we will be drawing. Okay, so we will now look at only what happens to first falling rate. Okay, that means it is the capillary controlled one and it is a straight line in nature. Okay, now here is the thing, the line could either pass through origin, so this is the origin 0 0, okay, or it can intersect some over here. Now in our case in your syllabus, we will consider up to when the line is passes through the origin. Okay, so other part is beyond our scope. We will not discuss in this, in your syllabus. Okay, so we will draw this. So this is the straight line. So we are not considering the curvature, because if you look at it, this one, if you, I am just extending this one. Let's say this is passing through this region, it will go through this point E. Okay, and this is just our sake of our derivation. Okay, here we have R. So this is RC. RC. So this is XB, XC. Okay, and E. This is the final point E. That means we are just assuming the falling rate only follow the first falling rate region. There is no diffusion control drying. All right. So assumption is that only one falling rate exists and it passes through, and let's say it is straight line. Come on. Straight line and passes through origin. Okay, passes through origin. So let's say this is up to E. Okay, that means we are finally reaching to the equilibrium moisture content. Okay, now what should be done? See, if you take any point over here and any point over here, let's say this is, okay, let's say this is XC equals to, here I am saying X2, right? And here it is X3, this is X4, and so on. Okay, because this is XB equals to X1 we have considered. All right. So what is the nature of this line? So let's say if you express this one, y equals to mx. So let's say slope is small a and this is x. Okay. So r equals to ax. All right. Is it clear? Because this is, here it is r, this is x, passing through origin, no intercept, r equals to ax. A is the slope of line. Okay. So we can write dr equals to a dx. Okay. Now we have dt. So this is the expression, you remember, minus ws by, what was that? A r dx, because the general expression is r equals to minus ws by a dx dt. So that's the general expression. All right. So this is the one. Okay, rather I would say this one I would rather write is as a, where is it? Okay. I would write it as a r. Okay, r. Okay, at constant rate period, r equals to rc. Okay, so this is the general expression actually. Okay, that I forgot to mention. So now what we will do? So dt equals to, okay, So this is dx. So minus ws by ar dr by a, right? Because this r is changing. Okay, so r is not constant. All right. So now what we will do, dt equals to minus ws by a dr by r. Okay. So let's say this is coming from T2 to some point T3. Okay. And here is, let's say it is, it is starting at RC actually. Okay. So if I take from RC to some point R3, so let's say this is the R3. Okay. So that means T3 minus T2, WS minus A capital A. So ln R, RC, R3. Okay. That is equals to minus WS by AA ln RC by R3. Right? Okay. So we can write. So this is, let's say, that delta T2 or delta T1, let's say. Delta T1 equals to minus, sorry, this has to be plus. Yeah. WS by, now A is R by X. Okay. So can we write A equals to, if you look at it, A equals to, so that means A is the slope. So slope here, 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 it remains same. So we can write A equals to also RC by XC, right? Equals to R3 by X3 and so on. Okay. So WS A capital A RC XC. Okay. ln RC by R3. Okay. So delta T on there, therefore this is the time requirement. Delta T1 equals to, let's say this is delta T2, because we had already had this zone, right? So this zone is, let's say, delta for delta T1, this is for the delta T2. Let's say this is delta T2. Okay. Delta T2. Okay. Sorry. WS XC by ARC ln RC by R3. Okay. Now we can further simplify this one, because we already know that RC by X equals to R3 by X3. Okay. Let's say RC by, from here, okay, XC equals to R3 by X3. That means RC by R3 equals to XC by X3. So delta T2 we can write XWX XC by ARC ln XC by X3. Okay. Now let's say we are taking, 3 over here. Okay. Now let's say assume the final moisture content is XF after the fast falling rate period. Okay. Say the final moisture content after fast falling rate period is XF. So what we will write? Delta T2 equals to WX XC by ARC ln XC by XF. This is the final expression. Any question? Okay. So today up to this. If you want to express in terms of thickness, the same thing. Okay. So delta T2. Let's say this is the time required for the falling rate period TF. Just I am mentioning. Okay. Equals to 2 delta rho S XC by RC ln XC by XF. Okay. So initially we had time for the constant rate TC, and we have also for the TF. Okay, TF equals to 2 delta rho S XC by ln XC by XF. All right. So total drying time T equals to TC plus TF. Any question? Any question? Okay. So if you do not have any question, so I need one more class. I'll just solve the problem in the next class and will give you the assignment. All right.
Okay, sir.
Okay. Any question? Okay. So if you do not have any questions, you can leave.
Thank you, sir.
Yeah.
Thank you, sir.